I think we're good. Be live. You
Okay.
can.
It takes a while for me to see that we're live. Uh, just, yep, we're live.
All right. Hello, everyone. Welcome to today's episode of Courtcast. I am your host, Tim.
And I'm Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, questions in the episode, and we'll get to it. So without further ado, let's get to it. So, Tim, last time I remember we did an episode 2 weeks ago or so, and we had talked about dimensions and various interesting things about them. And here we want to talk about like why is what's special about the number four? Like why couldn't the universe be less number of dimensions? Like what relative to that, why is four unique? So before we started, could you define what dimensions are very briefly and then like discuss sort of what is the crux of this episode? Like what is the main point we want to get across?
Yeah. So to recap a little bit, and two weeks ago, we described dimension. Um, the most basic thing about dimension is that this is sort of the space and time that we live in. These are what we call degrees of freedom. Like I can move my hands up, down, left, right, front, back, and also in time. So the freedom of movement in space and time. This is the dimensions that we're counting. But last episode, we also emphasized that it's more than that, because we believe there are some fundamental beauty about theoretical physics. So just having this freedom isn't enough. And we believe that there is this notion of symmetry, that's also associated with dimensions, meaning that up, down, left, right, front, back, and even time through Einstein's theory, they are all connected, one and the same object. And this is different from, let's say, a hunk of metal. Like we do not think we are living in a hunk of metal. We think that, at least in fundamental physics, we believe space-time is unique. It's a special thing, right? So, what is the crux about four dimension? Why four dimension? This is a question that physicists have tried to answer for a long time. And in summary, we don't exactly have a good answer. However, we have some hint that there may be reasons why four is special. There may be, some of that could be anthropic. Perhaps life might not exist if it wasn't four dimensional. There also are reasons why four might be kind of like a Goldilocks dimension. Maybe if it's too small, something bad would happen. Or maybe if it's too large, something bad might also happen. So in today's episode, we're going to talk about reasons why maybe if the number of dimensions are lower, some very bad things could happen to our universe. And this will be, I guess, part of a two-part series. This might help us explain why we live in a four-dimensional world.
Yeah, that's a good summary of it. So for this episode, we want to explore like the consequences of if the universe were lower dimensional. So why don't we start off by discussing like why does this all even matter to begin with? Why is it just say, oh, we live in four dimensions, we're done. Like when I learned in school and even intuitively, I knew we live in three dimensions and then one of time. And so why bother exploring this question even to begin with?
Yeah, and on the basic level, if you just look at the math, you might think that, oh, you know what, the math is similar, right? You write down a theory in three spatial plus one temporal dimension, the same math works for a lower dimensional thing. Like, is that the end of story? But it turns out it's a little more complicated. When you go to a lower dimensional world, sure, the math works out, but the physical consequences are different. Like it turns out that the types of particles and the number of particles that exist could differ drastically, and that includes the matter particles and the forces that those particles interact using. And particularly, I think the forces component is what matters. It turns out that if you go to a different dimensions, particularly lower ones, gravity and the other forces, electromagnetism, strong and the weak force, might look very, very different. And so different that we might not even see galaxies or planets and whatnot. And it is this lens where physicists, have made arguments that maybe 4 is special in that way.
Mm-hmm. So let's talk then about lower dimensions. So, for instance, let's walk through it. I don't know if it's good to start from, like 4 and go down, or if it's better to start from like 0 and work our way up and describe like how the universe would look like in various different capacities with different number of dimensions. So I'll leave it to you. What do you want to start with? Like 0 dimensions, which is the most obvious thing, or I don't know. Yeah.
Yeah, probably it's best to go to a lower dimensional world and kind of go to the basics first. Like
should we just start with 0 and work our way up, or start with 4 and work our way down?
Yeah, let's work our way from 0 to up.
Okay, so let's start with 0.
Yeah, and this is one of the most basic thing about dimensions, right? Dimensions kind of tells you your freedom of movement. It tells you how much freedom you have to move. In 0 dimensional world, there's basically nothing. But of course, there's one requisite dimension that we have to have. So we can't possibly have a 0 dimensional world. Usually when we say 0 dimensional, we mean 0 plus 1 dimensional. Time is always a given. There needs to be time, otherwise there's no change. If there's no change, there's no universe. So let's just say we're given 1 time dimension. I think that's a given. A 0 dimensional space, it just means that there's just 1 dot, like the dot is not going anywhere. Like there's like nowhere for it to go. Like there's nothing. So sure, you can have a universe like that, but the only thing you can have is kind of like existing versus not existing. There's not like a particle can't go anywhere. You can't even have the notion of velocity because it can't move. There's no place for it to move. So 0 dimension is just nothing. So at least we can say the universe is not 0 dimensional.
Yeah, no, that's fair. I mean, that case, that no-brainer case. And so it's just pretty much a dot that I guess you could say evolves in time, but it's like forces can't really exist because there's no velocities, there's no acceleration even, and so a force doesn't even make sense. Is that fair to say?
Yes.
Okay. So I think we've this list mentioned. So 1 plus 1, which to me is like a line essentially, and of course 1 dimension of time. So how does the universe look like in that case?
Right. So 1 spatial dimension, I think it's the smallest kinds of universe where interesting things can happen. And it's kind of like, and in this instance, particles just kind of, it's like waiting in a queue. Like if you're waiting in a line trying to get to a zoo, that's the 1 dimension, right? But imagine if the line that you're waiting in really is the entire world. Then that means you can't cut in line. You can't go back in line. Like if you decided to wait to get the ticket and you realize the line is like 5 hours long, well, you can't back out. You can't back out of it. You can't chicken out. You can't cut in line either. Like that's your whole life. So just kind of imagine this sort of particle world. In this universe, there is an absolute ordering of particles, one after another, waiting in line for eternity, right? So it's kind of a pretty restricted kind of universe. You can't even like move across one another without having interaction. Of course, like 1 particle can collide to the next, and then you start a nuclear reaction. Like it's like if you're waiting in line, in order for you to cut in front of the person, or in order for you to leave, you're gonna have to start a nuclear reaction. Like that's not exactly a pleasant universe, I would say. Certainly zoos won't be able to exist. So because that restriction, this absolute ordering, there's sort of like not too much wiggle room for particles yet. And as a result, we'll describe later, it turns out that in this low dimensional universe, forces like electromagnetism and gravity doesn't really exist, basically, because let me be precise a little bit. Like, you can have forces, but the notion of force carriers, like the particles of light and particles of gravity, does not exist in those universes.
Do you think it's better to explain more about that if we talk about a higher dimensional universe? Can you maybe
Yeah,
in this one dimensional, like why can't the force carrier of photon exist, for instance?
yeah. I think we can segue into that when we just accept the fact that, look, one spatial dimension is still a little restrictive. So let's
Mhm.
go to two, right?
Okay. Is that all before we move on, is that all you want to mention about like what one plus one? Could we talk about, let's say, like when you learn Newtonian mechanics, you learn the one over r squared law, and r squared, because the universe is 3 plus 1 dimensional, and so you have like it's like you imagine like a sphere, but in this case, I mean, what would be the one over r squared law in a 1 plus 1 dimensional universe?
Yeah, and you can kind of see some hint in the mathematics where some of the math breaks down, and I wouldn't say break down. Break down is a strong word. Like, some of the
Mhm.
math changes drastically when you reduce your number of dimensions to one spatial and one temporal, right? So take this one over r square law, for example. If you that's in 3 dimension, right? And if you go
Yeah.
one dimension lower, you get one over r, because the
Mhm.
force gets a little stronger. And the reason, and intuitively you can understand that, because volumes kind of increases as you increase the dimension. Because in 3 dimension, the concept of volume, it's like a ball, right? And in 2 dimension, the concept of volume is really area. So it gets smaller and smaller. And that's why, the forces get less diluted. So instead of 1 over r square, where r is the distance, it becomes 1 over r. And now if you extrapolate, this is for 2 dimensional world. If you have a 1 dimensional world, one spatial dimension, if you look at the math, 1 over r squared, 1 over r, then what? Is it 1 over nothing? This is kind of like, the math tells you something. And of course, when you work out the math, you do get different force laws, and it's a little different.
Mhm.
You can argue that it's maybe logarithmic, linear, whatever, right? But the math changes quite a bit, and it's telling you that, hey, look, something is different here. And indeed, 1 plus 1 dimensional quantum field theory actually is very special. And a subclass of these special theories are actually completely mathematically solved, mostly because particles has less freedom to move, and the math becomes more and more tractable. There's more and more symmetry, because space and
Mhm.
time really are on the same footing now, because you only have one spatial dimension and one temporal dimension. So
Mhm.
mathematically, there is many interesting things happening when you change dimensions.
Gotcha. Okay, so let's move to 2 plus 1 dimensions, two spatial, one of time. So now we've gone from a line to a sheet, like that evolves with time. So what does that look like?
Yeah, so the world become, I guess, a little bit more hospitable. Like, imagine if a bunch of friends are waiting in a line to go to the zoo.
Uh-huh.
If you decide to go home, you can actually go home. You can go around your other friends, and you don't have to start like a nuclear reaction just to cut in line and escape, right? However, the universe does have some restriction. So, for example, things that we take granted in 3 dimension does not exist anymore in 2 dimension. For example, the fact that I can tie a knot. If I'm going on a hike, I need to tie my shoelace. Well, guess what? The fact that we can tie our shoelace only works in 3 dimensional above. Like, if you, like, imagine you're on a plane, you try to draw lines, like, they can't cross. You can't go under. One rope cannot
Mhm.
go under another. So there are restrictions like that. So even though you can kind of walk around, but you can't how do I put this? This is kind of like in the mathematical study of topology. There's still enough restrictions about the spacetime, but okay, let's ignore that for a little bit. But at least in this universe, there is gravity. Electromagnetism comes alive now. You actually can have graviton. You can also have carriers of light. So this is a little closer to our universe.
Hmm. So you have graph and you can have like although piece of it. Maybe we could delve deep into that because it was interesting that you said, at least for electromagnetism, that the force carrier, the photon, doesn't really exist in 1+1 dimensional, but can exist in 2+1. So what actually changed?
Yeah. So, and this is actually somewhat non-intuitive, right? If you just think of the particles of light as a particle, you say, "Wow, gee, why couldn't it exist in the lower dimensional world?" But it turns out that as a particle, the particle of light, it's a little more than just a dot. And you can experience this in, let's say, polarization. Imagine you have polarized sunglasses, right? Depending on your orientation of your sunglasses, you can block particular types of light. So it turns out that light has an orientation. It has a little more structure in the particle itself. And if you go low and low dimension, that extra structure gets reduced. And when it gets reduced too much, that particle is almost like gone. Like it's just there's just not enough structure to it. And the same thing applies to gravity. Gravity has a little more structure than just a point-like particle. Well, graviton anyway. So when you change dimension, it turns out that the structures of these particles also change dramatically.
Mhm. And then maybe it might be helpful in the case of gravity to briefly mention the experiment that was used to detect gravity waves. Like, remember, there's two arms that detected like contractions and lengthening in like two different directions that only gravity has.
Yeah, sure. I think one thing to keep in mind is that these force carriers serves a function in our universe, in some sense, right? Like, for example, the particles of light, it's a messenger. It's a particle, but it also carries information. So what information does a particle of light carry? It carries information that tells how charged particles should move, right? And the way charged particles should move sort of comes in a direction. It's almost like imagine you're driving a car, and someone's asking you for directions. Your car is going in one direction, like a particle that's moving, but you also kind of have a mind. If somebody's asking you, oh, how do I get to the supermarket? You might say, well, gee, make a left or make a right. That's so the left and right is the extra structure on a particle of light. So, and if for those of you who are familiar, particle of light is made out of electromagnetic fields, and these have directions. And similarly, gravity serves a similar function. It tells how space and time stretches. And this stretching kind of has a direction, right? Like, and it's sort of analogous to, I don't know if you're familiar with these like funny mirrors, right? You can see, if you have one of the mirrors, you can see yourself being really fat or like really skinny, right? So gravity is kind of like that. It's telling you like, hey, look, I'm a graviton, and right now, space-time is going to stretch like a funny mirror. And, it carries information about how the orientation of that mirror. And when we detect gravitational wave, that's exactly why we need two arms, because gravity tends to the way space and time stretches, it tends to elongate one end and shorten the other, like a pulse. And that orientation can be used as a very important signal for gravitational wave detection. That's used. So these are important facts of our world.
Yeah, and so what? Okay, so I just want to really highlight the case that like, these force carrier particles are more than just like dots. They have a extra them with this polarization as you're talking about. If they didn't, if the graviton didn't have this extra, property to it, then you wouldn't necessarily need like the two arms to detect it in that sense. Like that wouldn't really matter. Is that fair to say?
Yeah, I think that's fair. And of course, you can argue that, gee, like, who cares? Like, does it matter for life that these force carriers have polarization? Like, is it really that important for our universe? Um,
Yeah, it's a fair question. You also mentioned very briefly, I mean, not that they mentioned, but in discussing this episode, we had talked about the case of an MRI as well that involves photon polarization to work.
yeah, exactly. So, so a lot of times the polarization aspects of these forces don't come into play, but some of our technologies are crucially dependent on it, even though a lot of people might not be aware. Um, and and light has a polarization, and this polarization actually helps it it manifests itself in the way it interacts with electrons. And one thing we mentioned in previous episodes is that electron also has spin. Electron is also not like a point-like particle. It also has a little more flair to it. It has a little bit more information than just being a dot. And that is
Mhm.
spin. And it turns out that you can use that spin to store information. For example, if it is spinning one direction versus another, that can
Mhm.
be used to create the digital analog of ones and zeros, right? And also that in atoms, electrons have the spin property, and you can use it for MRI machine magnetic imaging, right? In your bodies, you can manipulate the way the electrons are spinning, um, and by controlling it, you can measure a very particular type of light that it gets emitted from interacting with the spin. So if the particles of light does not have this extra polarization property, then this MRI machine is impossible. So like, you know, if we were to live in a 2+1 dimensional world, there would be no MRI machine, I guess. But
Yeah, that makes sense. So I just want to understand, make sure I understand this. Are you saying that like in 1+1 dimensions, a photon can't really have polarization? Because if I remember correctly from learning, polarization needs to be like not in the direction of motion. And so because of that fact, if there's only one direction to move, one spatial dimension, there's no other direction to point, so there wouldn't exist polarization of a photon. Hence, electromagnetism wouldn't exist in 1+1 dimension. Is that correct?
yeah, that's precisely the point. It's because there's no instruction, like there's no additional instruction for the photon. And yes, the mathematically photons have electromagnetic fields, and there's just not enough space for the field to go anywhere. It's so restrictive that there's just nowhere for it to go. Yeah, so in 1+1 dimension, there is no photon. But in 2+1 dimension, you start to have a little bit of freedom, because in addition to the direction a photon is traveling, it has an orthogonal direction, because it is two-dimensional after all. So a photon can finally exist. And I think similarly, for gravity as well, gravity can finally exist reasonably. Or graviton.
Mhm.
Yeah.
Mhm. I see. I see. Okay, so I guess like before we come to, the number of dimensions that we currently, observe, I guess is there any other like restrictions that you have on you?
Sorry, I think I missed the last part.
Oh, I said, is there any restrictions you have, more restrictions that you want to mention in 2+1 that you don't have in 3+1?
Um, yeah, I would say one thing though. in 2 plus 1 dimension, there's actually a very interesting phenomenon that is unique to 2 plus 1 dimension. And it is because of this phenomenon where when you pass over another person, you could, but it's not easy. What I mean by this is what I mean by this is this. Imagine you have a rope in this 2 plus 1 dimension, right? And you kind of tether to one end, and you kind of walk around it. If you walk around, depending how you walk around, you could create you could create like a massive, very complicated knot, and this has to do with the fact that the two-dimensional space, when you puncture it, is what we call non-simply connected. It means that the space has a hole that you cannot move around, and it creates obstruction in the world. And this does not happen in three-dimensional world. Imagine you remove a small chunk of your three-dimensional space, and you try to wrap a rope around that hole. Your rope would not get all tangled up. And this might seem silly, kind of like, oh, why does it matter? But it means that particles can carry this information of how many loops it goes around another particle, and there's all sorts of braiding and like interesting stuff going on. And anyhow, this means that there are new types of particles that can emerge. And I don't want to get into too much details, but in previous episode we talked about the duality between fermions and bosons, and it turns out that breaks down in for example 2 plus 1 dimension. That doesn't need to be the case anymore. So I guess the conclusion is sort of that, you would think you change dimension, no big deal, your math changes a little bit, but actually the physics drastically changes, the types of particle drastically changes, the type of forces drastically changes, and you might just end up in a totally unrecognizable world.
What about the case of like life itself? If we kind of, take it to the human realm, like what I guess what would be different? I guess we wouldn't really be able to see everything because things would look like lines to us. You can't really see a line. But apart from that, like I guess could life exist, or what? Yeah, just what would happen?
So I would say there's a bit of debate on this.
Mhm.
I think traditionally a lot of physicists thought that because gravity in 2 dimension is so modified, we just literally would not have a universe with galaxies and planets and things like that. So the way they do it, they can do a little bit of calculation. Oh, imagine you have some matter in the universe, and depending on the dimension, you see how, because gravity tend to clump things. You want to see, does gravity have the capability to create clumps like galaxies and then maybe solar systems so that things could live on it, right? Traditionally, it was thought that was impossible, basically. And it is true. If you just look at gravity itself, it is not possible to create such a environment. But I was just reading one paper earlier that people had proposed alternative gravity, where in addition to Einstein's gravity, you can add a little flare to it, some extra gravitational force that has no analog in our world. And when you do that, you could, they did the calculation, you could create structures like galaxies and planets, although also these are flat structures, right? And then you can argue, well, gee, maybe something complex could evolve out of it. Maybe there could be molecules and whatnot. But something as complex as humans, that's not obvious, I think.
Yeah, that definitely a contentious debate. Yeah, I guess so kind of more speculatively, I wanted to ask on the topic of galaxy formation. From what I know, galaxies are mostly in a plane. I mean, there are examples with the solar system like on its side, but effectively, like it's mostly a plane. I'm wondering in two dimensions, um, how would like dark matter be? Like, would it be clumped or like, yeah, just how would that look like essentially? If you, yeah, how does yeah dark matter play into this in
Yeah,
lower dimensions?
I don't think the research has gone that far yet because I mean,
Okay.
after all, two spatial dimensional universe is so we know it's not real. Like
Hmm.
we live in a 3+1 dimensional world, so people haven't gone that far in as opposed to like simulations of such a universe.
Hmm.
But I want to mention that even though galaxies look flat,
Yeah.
and you can say, well, gee, it looks flat. Isn't galaxy kind of two-dimensional?
Yeah.
Um, it's a fake two-dimensional, right?
Hmm.
And if you look at materials where people study like two-dimensional materials like graphene, if you cut your graphite into very one atom layer thick material, graphene, sure, from the perspective of the graphene, it is two-dimensional.
Hmm.
But it is not real because electromagnetism can still go to the extra dimension. And in the same
Hmm.
way, for galaxy, sure, galaxy is looks flat, but it still has the possibility to wobble, right? And in
Hmm.
fact, the need for dark matter, one reason why dark matter should exist is because galaxies has this instability to
Hmm.
wobble, to destroy itself. Without dark matter, the disk itself would kind of have too much wobbling, and it would disrupt itself. So it couldn't exist without dark matter. Um, but in a truly two-dimensional world, such thing does not exist. There's no leakage into the extra dimension because it just doesn't exist. Like, like a galaxy has no possibility of wobbling in that extra dimension. So I mean, you might not even need dark matter, possibly, right? In this world, and dark energy or all these things might look totally different. But I will add that many physicists, and myself included, I am not convinced that galaxies and stars and planets could form reasonably in this universe. I don't think I'm not sure if anyone has done like a really detailed calculation or thought of a universe like that. But I'm not convinced that can be done yet.
Yeah, that's a fair point. On the topic of materials, it's interesting because whenever I hear about people trying to study like what would like in lower dimensions, they use these materials like two-dimensional materials, one-dimensional materials, and it is true that those are approximate, but like, I mean, couldn't you use that as like a good proxy for, say, I remember when I was in grad school, there was a professor, I don't know the name of the professor, but somebody was studying like how gravity would be like in two dimensions by using like a two-dimensional material and seeing the gravity on it. Don't exactly know how the experiment was carried out, but plausibly, going along the train of thought, like couldn't we observe how proximate dimensions, or is it just like not even worth pursuing in that direction?
Yeah. So sorry, I missed the last part. I think
Oh, I said, are these experiments worthwhile to pursue? Like to take a two or one-dimensional material and see how like electromagnetism or how like gravity behaves in else.
yeah. I would just say that of course experimentally it's worthwhile because
Hmm.
we can write down theoretical models all day long, but
Hmm.
these universes do not exist. Like literally
Hmm.
do not exist. Like you can simulate it on computer and whatnot. Um,
Hmm.
but but really the material you can think of it as a simulation really at best.
Yeah.
Like if you were to kind of have a mock-up electromagnetism in the lower dimension, you can't exactly use the electromagnetism that we have in a higher dimension. Well, let me get this straight. Like you could use it, but it's not literally the same thing as like a lower dimensional electromagnetism.
Hmm.
Um, you may be able to fine tune it to create some kind of immersion in electromagnetism to see how that behaves. And of course, gravity, like you can't really test. Gravity is really weak in the lab. You can't really do that. You kind of have to create like a fake gravity in some sense that sort of looks gravitational. And ultimately, tests like that will only be approximate. It will never be exact, right? Whether that's worthwhile or not, of course it has, I think, value to test it out because the materials exist. Why not play with it and see what happens? But I don't think you will get the full answer on what a universe looks like in these lower dimensions, because I think that is something else. Like a universe is not a hunk of material as far as we experiments have shown us. So it is a good idea, but not sufficient.
Mhm. Can you expand further on like why can't you view the universe as like a hunk of material, for instance? Like what is so like I guess what separates space-time itself from like, a material? Maybe we haven't found the material, but like even in principle and also in practice, can you draw the distinction like why is it that the analogies between condensed matter materials and space-time breaks down?
Yeah, I would say this is, of course, this is very tantalizing, right? Because you can say, hey, look, and in some sense, on Earth, we're in a material, we're in air. We're not, there's not like nothing, right? So it's very tantalizing to think like, hey, maybe the universe is like a material. And from that perspective, dimensions almost don't matter because look, when you study, I don't know, let's say you study graphene, you can cut graphene up into one atom layer, and if you have one atom layer, I guess you could chop up your carbon and have one dimensional carbon chain, right? Something like that. And you will say, well, heck, maybe universe is just like that. We're just made of these little chunks of whatever universe atoms, and you can chop them up into lower dimension, high dimension, whatever, right? But we don't have experiments to support that, actually. And why is that? Every single material that gives us like a mock space time to play with, they are all kind of fragile, I would say. Like because like look, you look at a layer of graphene, it looks two-dimensional, but the moment you zoom into individual carbon atom, you can shoot a gamma ray at it and you can vaporize it. You easily see that, hey, look, the space-time is destroyed. And even the emergence of these particles, they are finicky to some extent. Like a lot of condensed matter experiments have to be done at very low temperature, very precise conditions to get it to work. But for space-time, that's not the case. We've tried very hard to break space-time. You shoot more and more energy at different particles, you try to break them apart. And we try to measure very precisely how, whether Einstein was wrong, whether space and time is really one and the same, whether the different directions in our universe is one and the same. In a material, the different directions absolutely are different. Like if you're imagining you're in graphene, you walk from one atom to the next, there's a location where one atom is relative to the next atom. There's a direction that's preferred. In our universe, we have not seen that. We try very, very, very hard. You zoom out very far, you zoom in very far. You don't see that. And like in our previous episode, this is what I mean by symmetry. There is an exact symmetry for us as far as we know. That is not approximate. That is not fragile. It's some of the most well-measured thing that humans have measured. So from those angles, our space-time dimensions, I would like to believe that they are indeed special, much more special than the artificial dimensions in a hunk of metal, for example.
Interesting. Yeah, that is that does make sense. I guess now coming to 3 plus and relative to lower number of dimensions, why would you say that that our current number of dimensions is special in that regard?
Yeah, I would say 3 plus 1 dimensions is the first instance. You're just starting to have enough dimensions to have really interesting physics. You can have particles that kind of get close, but then not collide and have cause a nuclear reaction. But they can get close and exchange particles and go on their merry way. You have force carriers that are sufficiently a little more sophisticated. You can have two polarization for light, and also gravity can have two polarization. And also, there's also one fact I hadn't mentioned. There's, I think, like a theorem in math. It has to do with some of the mathematical equations. Basically, imagine you were to hear a sound, let's say in 3 dimensions. The sound is very clear. In lower dimensions, in two spatial dimensions, the sound will get muddled because the waves are not spreading out enough, right? Well, that probably this applies to particles, waves of light as well. And so this problem, if you live in a lower dimensional world, it will be very, very noisy, very hard to get around, and the forces will be very restricted. And in 3 plus 1 dimension, it seems to be just kind of, you have just enough dimension, but not overwhelmingly so. Just enough dimensions to have very interesting phenomenon happening, to have complexity, and to have interesting interactions that are not so restrictive. And you can argue that from an anthropic point of view, this might be the reason why our world is 3 plus 1 dimensional, because it's the, if there's a overlord, a god or whatever, and they want, life or whatever to exist like this, at least go to 3 plus 1 dimension.
Yeah. So I guess one other question I have, a bit more abstract, is like, so dimensions we think about in terms of, like, as you mentioned, degrees of freedom, and we characterize in terms of 3 of space and 1 of time. But what if, like, there were fewer degrees of freedom than what we perceive in, like, more abstract dimensions? So for instance, like, the universe is really like 2 dimensions, 2 of these like abstract dimensions that are somehow related to space and time, but aren't like, it's not very clear what they are, but it just happens that this 3 plus 1 emerges out of that, but there are actually fewer degrees of freedom than what we're really seeing. What do you think about that possibility?
Right, and of course that people have contemplated that, and we do have something called the holographic principle that I don't exactly want to cover because it's very complicated. Previous episode, that that might not make sense anymore. So I wouldn't even call them the same dimension as what we have right now. So I would say, from that angle, if we define dimensions as the one we define dimensions as the things with locality, symmetry, and also like observability, easy to observe, then it really it's hard to imagine a lower dimensional world.
I see. I mean, it's kind of going off the point that, like, I mean, in a past episode, many, a while back, we had talked about how space-time itself is not fundamental. So I'm just curious, like, the thing to replace it with at a more fundamental level, does that have a notion of dimensions? Or maybe this is getting too off rails, but just curious.
Yeah, that's probably, at that level, it's not clear what dimensions even mean.
Okay.
Yeah, and let me just add that, like, for example, if you like the idea of string theory kind of flips on dimension on its head a little bit, because even space and times are made up of something else, made up of strings, and the dimensions, it got turned into something else, right? So what you mentioned, like, if you really zoom in, what is dimension? Yeah, that's that definition could drastically change depending on your specific theories.
I see. I see. So, okay. So that makes sense. So I realize we're at time. So I wanted to give you a chance to leave the audience with any, in our tradition, any words of wisdom that lower dimensions have taught you.
Yeah, I would say that traditionally, I think most of our episode always ends kind of in a humbling note. Be like, hey, look, the universe could have been way worse. Like could have been super inhospitable. Um, but the discussion on dimension is an interesting one because dimension is one of those things that's really discrete. I mean, there's 3 dimension and there's 4 dimension. Like they are really different. I guess you can say, well, maybe there's like 3.5, but um, let's not talk about that. Like, you can talk about fractals and whatnot, but it doesn't really make sense in that way. And it's interesting to think that, hey, maybe the universe had a choice at some point, and somehow, it chose 4. And if you go down this train of thought, what happens if dimensions were different? You can't help but feel a little bit kind of what is it? It's quite a blessing, to live in this 3 spatial dimension and 1 temporal dimension, right? Like, we live in a universe where we have enough freedom to do things. I think this is kind of like, I don't know, the constitution of the universe, the enough freedom to exist and move around and be happy in the universe. So that's I think that's a comforting thought, I think.
That's yeah, that's totally fair. I mean, I'm grateful to, be able to tie knots and whatnot. I don't know how I'd wear shoes in 2 dimensions. Or even like, yeah, like how would I move my feet? Anyway, that's a
Yeah, and you can wait in line in a zoo and decide to go home afterward. That's something to appreciate next time.
Yeah, yeah, yeah. So, yeah, and our next episode we'll talk about what happens if you have more dimensions, like why aren't there more dimensions, or if they are, what does that look like? And we've talked briefly about that, but we wanted to focus this episode solely on the lower number dimensions. So, on that, I want to thank everybody for joining us, and we'll see you all next week.
Yeah, see you all next week.